Ever felt like segment trees are too bulky for simple range sum queries? What if you could handle updates and prefix sums in logarithmic time with half the code? In this video, we will cover Fenwick Tree Binary Indexed Tree DSA practice questions range queries. Unlock the power of Fenwick Trees. Binary Indexed Trees for efficient range queries and point updates. In this session, we are diving deep into Fenwick Trees, also known as binary indexed trees. We'll tackle 30 high-yield practice questions designed to mimic real-world coding interviews and competitive programming challenges. Before we jump into the first question, make sure to hit that subscribe button to level up your DSA game. What is the primary purpose of a Fenwick tree, binary indexed tree? Option A. To perform constant time range minimum queries. Option B. To maintain prefix sums and handle point updates efficiently. Option C. To sort an array in O(n) time. Option D. To store strings for quick prefix matching. The correct answer is B. A Fenwick tree, or binary indexed tree, BIT, is specifically designed to handle prefix sum queries and point updates in logarithmic time. While a simple prefix sum array allows O(1) queries, updates take O(n). A BIT balances this by making both operations O(log n). This makes it ideal for scenarios where the underlying data changes frequently. It is not generally used for range minimum queries, RMQ, unless the data is monotonic, as it relies on the invertibility of the operation, like addition. In a one-indexed Fenwick tree, which bitwise operation is used to find the parent of a node during a query? Moving down the tree. Option A, I equals I plus I and I. Option B, I equals I and I. Option C, I equals I plus 1. Option D, I equals I caret I1. The correct answer is B. To calculate the prefix sum up to index I, we need to sum up the values stored in the Fenwick tree at specific indices. The rule for finding the next index to add is to remove the least significant bit, LSB, that is set to 1. The operation "I and I" isolates the LSB. By subtracting this from I equals I and I, we traverse to the next index that covers the preceding range. This process continues until I becomes 0. What is the space complexity of a Fenwick tree representing an array of size n? Option A, O(log n). Option B, O(n log n). Option C, oxygen mononitride. Option D, O(n squared). The correct answer is C. A Fenwick tree is typically implemented as an array of the same size as the input data, usually n+1 for one-based indexing. It does not require additional pointers or complex node structures like a segment tree might. Though segment trees are also O(n), they often require 4n space, because it only requires a single array of size n to store the cumulative frequencies or sums. Its space complexity is strictly linear. O(n). When updating a value at index I in a one-indexed bit, how is the next index to be updated determined? Option A, I equals I plus I and I. Option B, I equals I and I. Option C, I equals I asterisk 2. Option D, I equals I, 2. The correct answer is A. When we update a value at index I, we must update all indices in the bit that cover this index. In a one-indexed Fenwick tree, this is done by adding the least significant bit, LSB, to the current index, I plus equals I and I, . This moves us to the next responsible index in the structure. This operation continues until we exceed the bounds of the array, n, ensuring that the update propagates through the tree in O log n time. Which of the following operations is not natively supported by a standard Fenwick tree in O log n time without significant modification? Option A, point update. Option B, prefix sum query. Option C, range minimum query, RMQ. Option D, range sum query. The correct answer is C. A standard Fenwick tree is designed for cumulative operations where the operation is invertible. Like addition or multiplication, range sum queries are easily performed as query, R, query, L1, However, range minimum query, RMQ, is not natively supported in O log n for updates because minimum is not an invertible operation. While you can implement RMQ on a bit, updates would take O log squared n or involve complex logic. Segment trees are generally preferred for RMQ. What is the result of the bitwise expression I and I for I equals 12 ? Option A, 2. Option B, 4. Option C, 8. Option D, 0. The correct answer is B. The expression I and I is a trick to find the least significant bit, LSB, set to 1. For I equals 12 . The binary representation is 1100 . The 2's complement minus 12 is found by inverting the bits 0011 and adding 1, resulting in 0100 . Performing a bitwise in between 1100 and 0100 results in 0100 which is 4 in decimal. This value represents the range size covered by index 12 in a Fenwick tree. What is the time complexity to build a Fenwick tree from an existing array of size n using the most efficient method? Option A, O, n log n. Option B, oxygen mononitride. Option C, O, log n. Option D, O, n squared. The correct answer is B. While you can build a Fenwick tree by calling the update function n times, which takes O, n log n, it is possible to build it in O, n. You can do this by iterating through the array and adding the value of the current index to its immediate successor, parent, in the bit. Since each index is processed once and its parent is updated in constant time, the total complexity is O, n. If a Fenwick tree is one-indexed, what does the value at index 8, tree, 8, represent? Option A, the value at original array index 8 only. Option B, the sum of values from index 1 to 8. Option C, the sum of values from index 7 to 8. Option D, the sum of values from index 4 to 8. The correct answer is B. In a bit, index I stores the sum of the range I and I, for I equals 8 the LSB is 8, binary 1000 so $8 minus 8 equals $0. The range is 0, 8, which means tree 8 stores the sum of elements from index 1 to 8. This happens because 8 is a power of 2. And in bit structures, indices that are powers of 2 always store the prefix sum from the very beginning of the array. Why is a Fenwick tree often preferred over a segment tree for simple range sum queries? Option A. It has better asymptotic time complexity. Option B. It is easier to implement and has a lower constant factor in memory overhead. Option C. It can handle non-invertible operations like max, min better. Option D. It supports O1 updates. The correct answer is B. Both Fenwick trees and segment trees offer O log n for updates and queries. However, Fenwick trees are much more memory efficient, using n space versus 2n or 4n for segment trees, and are significantly easier to code. They also tend to have a smaller constant factor in practice, meaning they run slightly faster on real hardware for basic sum operations. Which index in a one-indexed bit would be the first to be updated if we call update? 5. Val. For an array of size 10? Option A, index 1. Option B, index 5. Option C, index 6. Option D, index 0. The correct answer is B. The update process always starts at the target index itself. When calling update, val, the very first element in the internal bit array to be modified is tree After updating index 5, the algorithm will then calculate the next index using I plus equals I and I, Since 5 is 0101 the LSB is 1. So the next index updated would be $5 plus 1 equals $6. Then $6 plus 2 equals $8. Then $8 plus 8 equals $16, which is out of bounds for n equals 10. To use a Fenwick tree for range updates and point queries, what transformation is required? Option A. Store the original values and use a bit for prefix sums. Option B. Use the bit on the difference array D, where D, I, equals A, I1. Option C. Use two 2D bits. Option D. It requires a lazy propagation segment tree. Bit cannot do this. The correct answer is B. By applying the bit to the difference array, a range update L, R, with value V becomes 2-point updates. Update, L, V, and update, R plus 1, V, A point query for the value at index I in the original array then becomes a simple prefix sum. Query in the bit, query, I, This is a classic trick to repurpose a bit for range updates. How many elements of the internal bit array are accessed during a query for the prefix sum of index 15 in an array of size 16? Option A, 1. Option B, 4. Option C, 15. Option D, 2. The correct answer is B. To query index 15, binary 1111 1. Start at 15, 1111 add tree 15, 2, $15, 15 and minus 15 equals 15 minus 1 equals $14. backquote 1110 backquote, add backquote tree, 14, backquote, 3, $14, 14 and minus 14, equals 14 minus 2 equals $12, backquote 1100 backquote, add backquote tree, 12, backquote, 4, $12, 12 and minus 12, equals 12 minus 4 equals $8, backquote 1000 backquote, add backquote tree, 8, backquote, 5, $8, 8 and minus 8, equals $0, total elements accessed, 15, 14, 12, and 8, that is 4 elements, which corresponds to the number of set bits in the binary representation of 15. In a 2D Fenwick tree of size mxn, what is the time complexity of a single point update? Option A, O, log m plus log n. Option B, O, log m asterisk n. Option C, O, log m asterisk log n. Option D, O, m asterisk n. The correct answer is C. In a 2D Fenwick tree, we nest the update logic. For an update at backquote x, y, backquote, we iterate through the x indices in O, log m, time, and for each x, we perform a standard Fenwick update on the y dimension in O, log n, time. This nesting results in a multiplicative complexity of O, log m asterisk log n. The same applies to queries. Fenwick trees are typically implemented using which underlying data structure? Option A, linked list. Option B, binary search tree. Option C, array. Option D, hash map. The correct answer is C. Fenwick trees are almost exclusively implemented using an array. This is because the tree structure is implicit in the bitwise relationships between the array indices. Using an array ensures contiguous memory access, which is highly efficient for cache performance and avoids the memory overhead of pointers. What happens if you try to use index 0 in a standard 1 indexed Fenwick tree implementation? Option A. It works perfectly as long as the array is large enough. Option B. The backquote update backquote and backquote query backquote functions will enter an infinite loop because backquote 0 and minus 0 backquote is 0. Option C. It will throw a division by 0 error. Option D. It will automatically be redirected to index 1. The correct answer is B. The logic of a bit relies on backquote I and I backquote. For backquote I equals 0 backquote, backquote 0 and 0 backquote is backquote 0 backquote. In the update function backquote I plus equals I and I backquote. If backquote I backquote is 0, it stays 0 forever, causing an infinite loop. Similarly, in the query function backquote I equals I and I backquote, it would also stay at 0. This is why bits are traditionally 1 indexed. Can a Fenwick tree be used to find the kth smallest element in a dynamic set of integers? Option A. No. This requires a balanced BST. Option B. Yes. By using the bit to store frequencies and performing a binary search over the prefix sums. Option C. Yes. But only if the integers are sorted. Option D. No. Because bit only supports sums. The correct answer is B. If we treat the indices of the bit as the values of the integers frequency array, We can find the kth smallest element by finding the smallest index I such that query I greater than equals k . This can be done in O log squared n using standard binary search or O log n using binary lifting on the bit structure itself. What is the total time complexity to perform M updates and Q range queries on a bit of size n? Option A, O, n plus M plus Q. Option B, O, M plus Q, log n. Option C, O, M log n plus Q. Option D, O, n log M plus Q. The correct answer is B. Each update takes O log n, and each query, which consists of two prefix sum queries, also takes O log n. Therefore, performing M updates and Q queries results in a total time complexity of O M log n plus Q log n, which simplifies to O M plus Q log n. In which of the following scenarios is a segment tree strictly more powerful than a Fenwick tree? Option A, when the range query operation is sum. Option B, when the range query operation is product modulo A prime. Option C, when we need to find the range minimum and the array elements can be updated to any value. Option D, when we only need prefix sums. The correct answer is C. Fenwick trees require the operation to be invertible, like addition, subtraction or multiplication, division. To calculate arbitrary ranges L, R, min and max operations are not invertible. If you update a value in a bit used for max, and the new value is smaller than the old one, the bit cannot easily recalculate the new max without re-examining other elements. Segment trees handle this naturally because they store the state of all subranges. Who is the Fenwick tree named after? Option A, Peter Fenwick. Option B, Alan Fenwick. Option C, John Fenwick. Option D, its developer at Google, Fenwick. The correct answer is A. The data structure was proposed by Peter Fenwick in his 1994 paper, A New Data Structure for Cumulative Frequency Tables. It became widely popular in competitive programming due to its efficiency and simplicity. The number of nodes in a Fenwick tree that need to be summed to get a prefix sum is equal to Option A, the depth of the tree. Option B, the number of set bits, ones, in the binary representation of the index. Option C, the number of trailing zeros in the binary representation. Option D, always log n. The correct answer is B. Because each step in the query function I equals I and I removes exactly one set bit from the binary representation of the index. The number of steps, and thus the number of array accesses, is exactly equal to the number of ones in the binary form of the query index. In the context of counting inversions in an array, how is the Fenwick tree utilized? Option A, by storing the array elements and sorting them. Option B, by using the bit as a frequency table and querying the number of elements already seen that are greater than the current element. Option C, by performing a range update for every inversion found. Option D, by building a 2D bit of array indices. The correct answer is B. To count inversions, Pairs where I less than j and a, I greater than a, j, we can iterate through the array. For each element, we count how many elements larger than it have already been processed and added to the bit. The bit stores frequencies of values. For an element x, the number of elements already seen that are greater than x is total elements processed, query x, then we update x, 1, to include the current element. Which of these is the correct C++ implementation for the LSB isolation? Option A, I and I1. Option B, I and I. Option C, I and I. Option D, I. The correct answer is C. The expression I and I uses the properties of 2's complement arithmetic to isolate the lowest set bit. For example, if I equals 6 110 minus 6 is 010 110 and 010 equals 010 which is 2. This is the standard, most concise way to implement this in C++, Java, and Python. What is the worst case number of operations for an update in a bit of size 1 million? Option A, 20. Option B, 1 million. Option C, 1000. Option D, 64. The correct answer is A. The number of operations is bounded by $log_2 n $. Since $2 equals $1,048,576. The log of 1 million is slightly less than 20. Thus, in the worst case, like updating index 1, it takes roughly 20 iterations to reach the end of the bit array. When using a Fenwick tree for range updates and range queries, why is the second bit multiplied by I? Option A, to handle the zero indexing offset. Option B, to distribute the update value across the remaining range indices linearly. Option C, it isn't. The first bit is multiplied by I. Option D, to account for the fact that a range update at L affects all subsequent prefix sums s_k, where k greater than equals L, by a factor of k, L plus 1. The correct answer is D. When we add v to a, L, R, the prefix sum $s_i for $i gel increases by $i L plus 1 CDOTV expanding this $i CDOTV L1 CDOTV the $i CDOTV part is handled by the first bit, storing $v and the $L1 CDOTV part is a constant corrective term handled by the second bit. In a Fenwick tree, what does a leaf node represent? Option A, indices with only one set bit. Option B, odd indices, 1, 3, 5, etc. Option C, indices that are powers of 2. Option D, indices at the end of the array. The correct answer is B. In the bit structure, odd indices are always leaf nodes. Why? Because the LSB of an odd number is always 1. The 2 to the power of 0 bit, since $I, and I, for an odd number $I is just $I $1. And $I plus I and I Dollar is $I plus $1. Odd indices only store their own value and do not cover any other indices below them. Which of the following is true regarding zero-indexed Fenwick tree implementations? Option A. They are the standard and preferred method. Option B. They require using I plus 1, and I plus 1 to navigate. Option C. They are exactly the same as one indexed, just starting at 0. Option D. They are impossible due to bitwise logic. The correct answer is B. While one indexed is standard because of the simplicity of I and I, zero-indexed versions exist. They use slightly different bitwise logic to avoid the infinite loop at 0 problem. However, most practitioners find it easier to simply use a one-sized larger array and ignore index 0. Compared to a square root decomposition, Mohs algorithm, a Fenwick tree is: Option A. Slower but uses less memory. Option B. Faster for updates and queries. Log n versus sqrtn. Option C. Equally fast but harder to implement. Option D. Only useful for offline queries. The correct answer is B. Square root decomposition typically offers O1 or O-sqrtn updates and O-sqrtn queries. Fenwick trees offer O-log n for both, since log n is much smaller than sqrtn for large n. Bits are significantly faster for standard range sum problems. However, sqrt decomposition is more flexible for non-associative operations. If we want to maintain the XOR sum of ranges with point updates, can we use a Fenwick tree? Option A. No. XOR is not supported. Option B. Yes, because XOR is its own inverse. Option C. Yes, but only for range updates. Option D. No, bit only works for addition. The correct answer is B. A Fenwick tree works for any binary operation $s asterisk $, as long as the operation is associative and has an inverse. XOR is associative $. O plus B, O plus C equals A, O plus B, O plus C, $, and it is its own inverse $. O plus B, O plus B equals a $. Therefore, you can replace the plus with in the bit implementation to handle range XOR queries perfectly. That wraps up our 30-question deep dive into Fenwick trees. From basic implementation to 2D applications and inversion counting, you've covered a lot of ground today. If you found these explanations helpful, give this video a thumbs up and comment "Bitmaster" below to let me know you finished. For the complete practice set and detailed certification resources, check the link in the description below.